The solubility product. Attention! In these experiments, toxic, caustic and irritating compounds are handled. I don't take any responsibility for damage done to persons or property caused by the replication of these experiments. When a salt like sodium chloride is added to water, its ions go into solution. Smaller amounts of it are dissolved completely according to the following equation, and an unsaturated solution is formed. Nevertheless, in reality, it is a chemical equilibrium which is completely on the right side, so that no more solid sodium chloride is present. When more is added, a point is reached where the additional salt doesn't dissolve anymore in the solvent. Then this is called a saturated solution. At this point, the dissolved ions are in an equilibrium with the solid. The law of mass action for such an equilibrium looks as follows. The equilibrium constant K is the product of the concentrations of the ions, which is divided by the concentration of the salt. The undissolved salt is a solid, hence its concentration is not important for the equilibrium. There is no difference if 1 gram or 10 grams of salt are at the bottom of the beaker. When the constant K is substituted by Kl, L or Ksp as in some books, this is the equation of the solubility product. To show its influence, 2 test tubes are filled with a saturated sodium chloride solution. In the saturated solution, the product of the concentrations of the ions corresponds to the solubility product of sodium chloride. When the concentration of one of the ions is increased, the product becomes larger than the solubility product, causing the solution to be supersaturated. This can be achieved when concentrated hydrochloric acid is added to the sodium chloride solution. This increases the concentration of the chloride ions, and salt precipitates until the concentrations of the ions give the solubility product again. The same effect takes place when saturated sodium hydroxide solution is added, which increases the concentration of the sodium ions. Exceeding the solubility product is part of many tests in chemistry. In these, salts are often formed which have a very low solubility product, as for example lead-2 iodide when adding sodium iodide to a solution of lead salt. The stoichiometric values are used as exponents in the solubility product. So supersaturated solutions are immediately balanced out by precipitation of a part of the dissolved salt. The solubility product depends on temperature, which is why the values are usually given for a temperature of 25 degrees C. That's why many salts dissolve better when the solvent is heated, because the solubility product is also increased. When the solution cools down, the solubility product is decreased, causing salt to precipitate again. Nevertheless, it is also possible for the salt not to precipitate immediately from a supersaturated solution. For this, some sodium acetate trihydrate was heated with a very small amount of distilled water to replace evaporating water. When all of the crystals had dissolved, the beaker was covered and set aside. When this solution cools down, it often forms a supersaturated solution due to the lack of seed crystals. This is a metastable state, so movement, dust particles or the addition of seed crystals can cause the crystallization to take place. Here the crystallization began after the cover had been removed. In the crystallization, energy is released in the form of heat, which is why the effect is used in reusable hand warmers. Here is a summary. The solubility product is calculated with the concentration of the ions of the salt, and stoichiometric factors are used as exponents. When the product of the concentrations is smaller, equal to or higher than the solubility product of the salt, the solution is unsaturated, saturated or supersaturated. The solubility product depends on the temperature, which is why tables usually contain the value at 25 degrees C, so it has to be taken care for what temperature the value is given. This was the solubility product. I hope you enjoyed. Please rate and comment. If you want to see more theory of the solubility product, you can watch my video here, or you can watch my latest video here. A big thanks to my supporters on Patreon.